Indeed, well, first I would like to thank organizers to invite me here to Tokyo, this nice place, this nice conference. And indeed, I changed the title since I'm the last one before the hot topics. I thought I should also add some hot topic, at least some new stuff. So I split my talk in two, and will the first part talk about secure long distance QKD, and the second part about what we believe provably secure steganography. So, well, the first part is essentially this paper here, and I should highlight the contribution of the first author, so Boris, who made most of the experimental work, and Charles, who made the theory proofs and so on. So the system, well, if you want to make a long-distance QKD experiment, you need a few ingredients, and one ingredient is to have an efficient scheme. And efficient means it should, if you go to high distances, it should be robust against photon number splitting attacks. The scheme we use is this cow scheme, so the coherent one-way scheme, which I explain very, very briefly without going too much in details. So we have here, we have here a CW laser. Then we randomly modulate this intensity modulator in order to cut out a series of pulses. And then we have a convention that when the photon is in the first pulse, then it's a bit 0. If it's in the second pulse, a bit 1. And for security reasons, from time to time, we send 2 pulses, which we call a decoy sequence. And of course, we attenuate this, send it to Bob. So Bob, on his side, well, he just detects the arrival of pulses and can say if it's a 0 or a 1. Now, of course, this wouldn't be like secure like this. For this reason, we add also here an interferometer. So some part of a light goes to the interferometer, and here we can look at interference between succeeding pulses. So if you want to estimate the influence of information of an eavesdropper, what we do, we measure here the quantum bit error rate in this data line, but then we also measure visibility here. And the idea is, whenever an eavesdropper tries to measure the position of this photon here, for instance, he will destroy this coherence between these 2 pulses. And then if these 2 pulses go here to the interferometer, the visibility will be reduced. So we adjust the phase in this interferometer in a way that if there is no eavesdropper, all light goes out here, and when there's the eavesdropper is coming, it goes to the detector, and it's kind of a information where there's an eavesdropper. That's the idea. Now, why is it quite robust against photon number splitting attacks? Well, photon number splitting attacks are efficient if an eavesdropper can act on different qubits in a different way. So whenever he finds a qubit or a pulse with 2 photons in it, she would like to keep these pulses, take one photon out, send the other to Bob, and block the other pulses. So if she tries to do this on these pulses here, let's say she finds 2 pulses here, of course then 2 photons here, she will destroy also the coherence. Or she should also remove this pulse. She cannot just particularly act on one qubit, which makes this attack much less efficient. Okay, so once you have determined quantum bit error rate and visibility, you can have an information about the action of eavesdropper, and you put into key distillation. No? And now, if you want to make this key distillation, of course, you need also a very good protocol and a precise way to estimate the information of Eve. And it's important that you take into account the finite key effects. No? Indeed, if your sample size is very small, statistical fluctuation could lead to, in a way that your estimation of Eve's information is very bad. And there was a considerable success or improvement in the way you can estimate this information. And you see here red and blue curves, and this shows you the improvement we made with a new analysis. No? So the new analysis is these solid red curves. The blue one is the previous analysis. And you see a couple of curves, and they correspond to different block sizes of these post-processing blocks. So it starts by 10 to 4, 10 to 5, and so on. And of course, the more you go to higher block size, you approach this asymptotic limit. So if you have, of course, very long keys, then it doesn't matter. But if you want to operate with reasonable block size, you see the difference can be huge. No? For instance, let's take this example here. With the old analysis, we could go to 170 kilometers. With the new one, we could go to 220. So that's also an important element. Now, a third element, and it's probably know that, it's probably the most important, is actually with very low noise detectors. And you see here, well, roughly, if this, the secret key rate is a function of distance. Suppose you have 100 counts per second dark count rates, or 1 count per second. So you give 1 count, you go over 300 kilometers, 100 counts, you 200 something. And the reason is obvious somehow. You see here on down below, see the quantum bit error rate. We have a constant error rate, which is due, what we call optical error rate, which is due to imperfect alignment of your system. But then you have a variable one, which is the detector rate due to the noise of a detector, dark count rate, error rate due to the noise of the detector, which increases if your signal goes down. And you see this, now this quantum bit error rate increases, of course, and at some point you cannot no longer distill a key. Well, so our requirements are we would like to have very low dark count rate, but we also would like to have a compact detector, no? So since that's why we wouldn't like to use SSPDs. We would like to use APDs. And APDs, they have another problem. And this is this afterpulsing, which Nicolas Brunner just mentioned before. No? And this adds some additional loss, so we also have to find a way to control these afterpulses. So I will go a bit more detail what this is, afterpulsing. Not too much, don't be afraid. So if you, in these avalanche photodiodes, no, if you absorb, first you absorb a photon, and then the electron goes to this multiplication reaction, and you make an avalanche. You end up with a macroscopic signal you can detect. Now what happens that in this multiplication region, some of these charges can be trapped and eventually released later on, what you see here. And they also generate an avalanche, which you cannot distinguish between the real avalanche from provoked by a photon. So this is noise, no? And one thing we realize is the more or bigger the current is that flows through this region, the more charges are trapped, and the higher is the probability to get an afterpulse. So if you want to reduce this, you have to reduce the current to go through. So what do? We use a special diode, and here I will really not go into the details, but this special diode has a resistor inside, and this makes that it quenches very rapidly the current once you have a detection, and makes that you have relatively low afterpulsing. And so if you have this rapid passive quenching, and moreover you can add some hold-off time, you can wait a bit after each detection, you can have low afterpulsing. And these detectors are also very nice on the level of dark counts. No? You see that with this kind of detectors, we get 1 dark count per second at 10% efficiency and at a reasonable temperature of -100 degrees. You can read more about this in these papers here. Okay, now it's just something I would like to mention. There's a trade-off you have to make. If you want to reduce the dark counts, you would like to go to low temperatures, but it turns out that these afterpulsing probabilities increase. So you have this trade-off depending on if you need very, very low noise, so if you had long distances, you would cool down more, no? And then, but afterpulsing increase, but you compensate this with this hold-off time I just mentioned before, no? So, and it goes in a good way, no? If you go far away, we have little detections, and you can afford to have hold-off times between the detections because there are not that many. So this means that actually we will, as a function of distance, we will tune the temperature of our detectors to get optimal performance. Okay, the fourth ingredient is, of course, good optical fibers. And we got our fibers from Corning. And I would like to go into details to have all these different coefficients of absorption. The main message is that these guys make a very good work, and all these coefficients are essentially negligible. So for instance, this absorption due to OH, it's nowadays no longer a problem. What remains is this Rayleigh scattering here. And here, of course, it's a more physical thing. No, you cannot reduce it easily, but nevertheless, if you choose the optimum dopant concentration, you can put this to the minimum level. And you see here the kind of fibers that are available, and we are using this ultra low loss fiber over here. And we can have attenuation down to 0.016 dBs per kilometer, which is a very good value because most of the normal installed fibers are here. So this means that we don't use installed fibers. We have just in our lab these spools of these very nice fibers. So the people who want to make QKD in cars, as we heard on Monday, they may be a bit afraid about the size of this box. But I can tell you that if you take your trusted car, actually the fibers fit in it. So it's no problem. Now, okay, we have all the stuff, and we put everything together. And you see here now how our prototype looks like. No, we have this, oops, sorry, I always have the same problem as most of the speakers. So you have these boxes, 19-inch boxes, and of course some fiber in between. And here in this case, actually, these detectors we use are not in the box because we have a bigger cooler. So you can see a bit inside the box how it looks like. Well, without going in all the details, you see here actually the optical elements I showed you before on my first slide when I explained to you how we work with attenuators and so on. And then you see we have two fibers. So we have one fiber where we send a quantum signal, and the other fibers we use to synchronize the two machines. And here you see the cooler. It's a Stirling cooler. It's a box maybe big like this. And then you see all this black thing here. This may be something you cannot really recognize from behind. But this is actually all what we do in a FPGA. So this is a very essential element of our system because to handle signals at this speed of 1.25 gigahertz is our clock rate, to handle all the synchronization, the delays of the detectors and all this stuff, and also the distillation actually, the error correction, those things, it's very important that you can do that in hardware. Okay, so let's have a look at the results. So you see here the obtained secret key rates as a function of fiber length. And you see, well, it starts at 13 kilobits, something around 100 kilometers, and we have still 3 bits per second at 300 kilometers. And these curves show you how we change the temperature. So if we, at this point, we will use 153 Kelvin, and if we kept this temperature, actually here, we wouldn't go that high. That's why at shorter distance, we lose a slightly higher temperature. And the reason is, of course, we change many, many parameters. No? It's really an optimization. And we just show a few of them to give you an idea. So see, for instance, here it's our detectors. No? We have efficiency and this hold-off time. So if you go, let's start here. If you go to a very long distance, we can put a very long hold-off time. No? That's a thing what we do. So then, of course, if you do this, we cannot have high count rates, but that's not the problem here. That's why, but here we are saturating, no? On this curve, 153 Kelvin. On the other hand, if you go to short distances, we reduce the hold-off time, no? And now, well, it's a bit funny. Actually, you see here, we also go down with the efficiency here a bit, because if you lower efficiency means also lower noise, which allows us to go a bit further. But you see, well, here I have 27, 22. At short distance, we all have 22. And the reason is here because we start to saturate our detectors. So there's no reason to have high efficiency. But that's just to show you how we can tweak all these elements. And another thing is, for instance, this block size for post-processing. Of course, at the beginning, we have very high rates, so we have very high block sizes, 2 times 10 to the 7. This means that we have to wait 500 seconds before we can start one round of distillation. And if we go far away, we have to use smaller block size. No? This means that we have to give a bit more information to Eve. No? We have to make more privacy amplification. But if we choose the longer block size, it will take too much time before we can start distillation. No? You see, we choose a block size of 6.6 10 to the minus 5, and then we have to wait 17,000 seconds. So here you see one run over 200 kilometers, 70 hours. You see here the secret key rate, and you see here below, you see the quantum bit error rate, and here the visibility. Of course, it fluctuates a bit, but online, we tune our system to stabilize it. No? So of course, we use the quantum bit error rate to adjust things like the temporal alignment and so on. And we also optimize the visibility all the time. Now, if you look at the run over 300 kilometers, you see it looks like this. So you see now a quantum bit error rate is a bit higher than before, obviously, it's 3%. And here you see the error rates in our monitor detector, which also fluctuates a bit. And you see it actually, we make this run over 4.5 hours, and that's the time we need to fill our block for post-distillation. Okay, so maybe I would like to summarize this first part. Well, there are many experiments were made on long distances, and I think the two things which characterize the best our system is that if you look at this list here, that actually, if you look at those experiments over the longest distances, most of them use this superconducting detectors, and our experiment can run with in-gas detector, which is, of course, a big advantage. And another thing, maybe another feature I would like to highlight is that of all these systems, we are the only one who actually made a finite key analysis and can give some quantifiable security statement. Okay, so let's come to my second part about quantum secure steganography. So this is very recent work. We just put the paper on arXiv 2 weeks ago. And it was essentially led by Bruno and Anthony, and we also got some help from some mathematicians, from Julia, who is now working in Darmstadt, in Professor Buchmann's group. And it's very new, and of course, to be honest, I don't understand a lot about steganography. And it's really a big field for essentially mathematicians, so please, we are physicists, and I want just to suggest a physicist's approach and solution, how we can do that, no? Okay, well, of course, probably you know what steganography is. It's just a way, if you want to hide a message, a secret message in some message or something that looks very normal, no? Probably there are many methods to do this. Maybe you have, as a child, you played with this unvisible inks, no? For instance, that's a way you could make steganography. And of course, we have to distinguish it from cryptography, because cryptography guarantees the secrecy of a message, but not the privacy, no? So if I send a random numbers to somebody, of course, you can see that I sent something, no? And of course, nowadays, you know, if all the transfer of data is supervised and so on, the very fact that you send something encrypted to somebody may make you suspicious. And in different countries, you can have big problems, no? And I would just remind you that Universal Declaration of Human Rights in its Article 19 guarantees a freedom of opinion, but also a freedom to communicate. And the bigger the big brother becomes, I think, the bigger is the interest to think about steganography. Okay, that is a motivation. Now, how does it work normally? No? The idea is, well, normally there are many ways, as I said, but most schemes concentrate to hide some information in a picture. So you start with what one calls a cover image. It's a not very nice picture, but any picture, no? And then you have your clear text, and you make some transformation and send it over the internet somewhere. Of course, here we have this, you generate this stego image S, which should look like any random image. You should not find out that it hides something. And then Bob on the other side, of course, with his computer again, can extract the clear text. That's the idea. Now, in our case, we would like to base the security on the quantum noise in light, no, the shot noise. So if you take a picture with a modern CCD camera, each pixel will get some amount of light. And if you repeat that many, many times, you will actually get a histogram of a number of electrons you detect in your camera. No? And you see this, I'm very stupid, sorry. You see this distribution here, which is a nice Poissonian or Gaussian distribution. And what's interesting also that you see that if you don't send any light, this distribution is very narrow. Huh? So nowadays, in good cameras, the shot noise is much higher than the noise you might have, electronic noise. This means that you can take profit of this randomness here, and you can, for instance, use that to extract random numbers. No? That's what we did in this paper which appeared, oh, that's an error, 2014, last year, no? Okay, now we don't want to extract randomness, but we want to take profit of this random distribution of values we have in one pixel. No? So actually, this means if you have a pixel, no, per pixel, let's say you have 16 bits or 12 bits, whatever. Since this width here goes roughly with a square root of number of electrons, no? This means for this 12 bits, actually 6 bits are roughly 6 bits, half of them are random, no? So we try to play with these random bits. Okay, so one very naive idea would be so, okay, I just use the last one, and depending what I want to encode, I change the bit number, or just the last bit, I flip the last bit, no? Well, that's a bit naive, because if you have a camera, no, a real camera, you could have, for instance, dead pixels, no? So if you take pictures and you have a dead pixel, all of a sudden this dead pixel doesn't have 0, but 1. It's strange, no? But you can also have a picture where you saturate a few pixels, and instead of having 1, 1, 1, 1, 1, 1, all of a sudden you will have 1, 1, 1, 1, 0. Huh? Doesn't work. Of course, now we can pay attention to that, but still, it's still not work, no? I would like to show you here. So let's suppose you have a picture where you have quite a big area which is very homogeneous. No? We take a picture of your girlfriend at the beach, has a very nice blue sky. This is a very homogeneous illumination. And of course, you can make statistics on this, and you will find a distribution as I showed you before, no? Something like this, no? So this is a simulation, no? For a certain number of events and so on. But you see, it's kind of a Gaussian distribution, no? But now if you just swap the last bit randomly, no? Actually, we'll average between two adjacent points here, no? And if you make now the statistics again, you see this, no? So the bad guy, or the good guy, it depends, no? But he will just make statistics on your picture, and we'll see something like this instead of something like this. And he will discover it. Of course, this is assuming that the big part of your picture is really homogeneous and so on. But it should show you that, of course, if a more complicated picture, it will not so be easy, the statistics and so good, but I just want to show you it cannot work. Because we want a perfectly secure way. No? Okay, so what could be a better idea? Now, well, the idea is actually we take two photographs very quickly, one after the other. And of course, we need some assumptions for this. And we say, okay, the state of the object and the state of the camera hasn't changed. So we have two photographs, and the difference between these two photographs is just due to the quantum randomness due to short noise. No? And now, well, another assumption is also we should not have too much crosstalk between a pixel. But actually, well, if you think about it, it's not even that a big problem. But anyway, it's also something which is certainly not good if you have too much correlations. And now we have a protocol, no? And the protocol goes as follows. I have text T, and I want to create my Steganography picture S. And I do it like this. So I have my bit, my pixel E, no? I take it from picture 1, which we call now the key picture, if T is 0, or I can take it from the other picture, which I call my cover picture, if T is 1. Like this, very simple, no? And now on the other side, Bob, he has a key picture, and he can look at the cover picture and makes inverse reasoning, no? Whenever he can read the text, no? He looks if this, but no, sorry, the Steganography picture, the cover picture, we don't need anymore, no? But the Steganography picture, which is sent to Bob, he compares it with his keys, and whenever if it's equal, then of course it knows it's 0 and it's not equal, it's a 1. And of course the point is that this Steganography picture cannot be distinguished from any real photograph. It's just two realizations of the same situation which are mixed up. Okay. Now, okay, that's the way it works, no? So that's why how I communicate, let's say, with my wife, no? We went to vacation to Iceland. We took lots of pictures. We share them on our hard disk. And then I took a plane to Japan. And now if she wants to send me a very secret message, no? She takes her text, calculates the Steganography image, and puts it on, let's say, Flickr. And now in my hotel room, I go to Flickr, download a picture from Flickr, and calculate the clear text. That's the way it should work. Okay. Well, how we make the experiments? Of course, we are an experimental group. So we tested a few cameras, monochrome scientific camera, and also consumer color and cameras. And one important thing, of course, you better start with raw image files, no? Obviously. So in our case, we have 8 megapixels, 16-bit TIFF files. And that's a kind of test picture we use, no? It's a PCB of one of our apparatus we construct in Geneva. And it's a strange picture, but it's a good picture because it's a huge contrast, no? You have these bands here which are reflective, and we will saturate a lot our detectors from time to time. And if you saturate, well, something I didn't mention actually, no? Whoops. No, if you saturate the detectors, some pixels, of course you have some chance that actually SE equals to key E, because both are saturated. And this, when it should not be the case, no? And this introduces errors. That's why, sorry, I'm going the wrong direction. That's why we have to implement error code, no? So we implement the Reed-Solomon code and so on. And so that's this kind of pictures allows us very well to test our error correction code, no? Okay, so now the result, well, it actually works. Now, it's not so, I cannot give some bit rates, whatever, but it works. First of all, we realize that we don't have cross-pixel correlation, so this is a kind of an autocorrelation function in our experiment between the one pixel and all the others around, and you see the experimental data and simulated data, and it's roughly the same. Right? So this doesn't seem to be a problem. Well, then, of course, the stability depends a bit, no? That's a bit a tricky thing, no? In our lab, if everything is stable, it works, but we're not quite sure how it could work if you make it just outside the picture. Probably should pay attention. They don't take a picture of a bird who's flying across a picture, something like this, no? That's a bit more tricky. What's also quite tricky is actually the treatment of color images, no? Because they have 3 pixels for each color, and then you have this white balance, and there are many things interfere. But it seems, we cannot really tell it, it's very easy, but it seems it should also be possible with color pictures. And this also should be possible with JPEG fields, actually. Just, of course, with JPEG averages of a few pixels, so you have less data you can hide in one picture. Okay, so I come to my conclusions. Well, we have seen this picture before, no? But of course, you didn't realize that it was actually a key picture. And this is also something you don't realize. It's a stego picture, no? But it looks like a normal picture, no? So now if I want to decrypt this, I can launch my algorithm, no? And you can see the conclusions. Okay, so conclusions are very short, no? I showed you this experiment over 300 kilometers, and, well, we think at some point, of course, it can still go on, but probably for reasonable effort and reasonable development of optical fibers, the limit is close to be reached, no? And so we actually more focus now on get faster signals systems or smaller systems, no? And I would like to show you just, that's what we have now, no? Made this system I showed you in this 19 reaction more compact. And this one actually contains also the detectors. We don't have a very cold detectors, but normal detectors can fit to it. So that's certainly one development that should be made. And, well, this proofly secure steganography, we are really at the very beginning. I hope I could convince you or at least interest you in this field. And yeah, that's it. Thank you very much.
Any questions? I have a comment. So essentially, you hide a one-time pad using steganography. Indeed.
We use a one-time pad protocol, indeed. And the key is image. And again, like one-time pad, you should use the key image only once, and it has as many pixels as your text can be, no? Obviously.
Any other questions? I shouldn't ask a question. Yes.
You're saying that the ultimate reasonable limit is 400 kilometers. I remember to have seen, I think it was Grégoire, but I mean, in a 2000 speech by Ide Kantik, one of my first exposure to quantum cryptography, and the ultimate limit was about 150 kilometers or so. So
well, I think we already now we know how to go to 350 kilometers. Okay. Proving this and that, roughly. And then, well, another 50 kilometers are another 10 dB loss. So, of course, maybe you can bit further, but the bit rate inevitably goes down. So, at some point, anyway, it's no longer very interesting.
I have a question. The Rayleigh scattering is because the fiber is basically an amorphous material. Mm-hmm. In principle, if you could make a crystalline optical fiber, you might get much less loss. Has anyone thought about that?
Yeah, of course there is very different approaches. Now also these hollow car fibers, you could make fibers with essentially most of a part of a beam is actually in air. And there are different approaches. You could in principle go further. And if you talk with these guys from Corning, they are quite optimistic that they could go maybe 0.1 at some day.
All right, well, if there are no more questions, let's thank Hugo again.